Section 3.2 problems. Problem 1. The exponent on the variables in a polynomial function must be non-negative integers. That is exactly correct. No negative integers allowed, no fractions allowed, whether they're positive or negative fractions, no irrational numbers allowed. The exponents of every term, they can be 0 and they can be positive integers, and that is all. And that is for every single polynomial function out there. That's one of the classifications of polynomials. The graph of a polynomial function may have a sharp corner, and that is a never. If it's a polynomial, this is one of the characteristics of them. They are smooth and rounded like a roller coaster, and that is an always for every single polynomial function that's out there. Okay, some problems. Use the leading coefficient test to determine the end behavior of the graph of each function. Okay, so here we got the polynomial function x to the fourth minus 4x squared. So f of x equals x to the fourth minus 4x squared. Okay, quickly scan the whole thing. Pick up the term of highest degree. That's x to the fourth. Okay, the number in front here is positive 1. So if we think this through, when x is large and positive, the fourth power will make it also positive times positive 1. So this will go up on the right side. But a large negative number to the fourth power is also positive, and positive times positive 1 is resultant positive. So it'll go up to the left as well. So the only details that we know here are up to the right and up to the left, but we don't know anything about what goes on there. Only the far end behavior. Okay, what's the next one? F of x is equal to 2x cubed times x minus 1 times x plus 5. Okay, so take a look at that. F of x is equal to 2x cubed times x minus 1 times x plus 5. Okay, so here the lead term is not very obvious, so we're going to have to work on obtaining it. Now here we have x as your highest power, so the other stuff doesn't matter. Here we have also x as your highest power. The rest of the stuff doesn't matter. When I say it doesn't matter for the lead term test. So if we imagine multiplying it out, you'd have 2x cubed times an x contributing from this parentheses times another x contributing from that parenthesis. So that'll give us 2x to the 3, 4, 5, 2x to the fifth. Okay, 2x to the fifth. So there's your lead term. Now we have odd degree. Odd degree will have opposite end behavior. When x is positive and large, fifth power makes it positive, n times positive 2 also makes it positive. So that's going to go up to the right. When x is large negative, a large negative to the fifth power is negative. Negative. Times plus 2 will result in a negative, so that'll go down on the left. There's your opposite end behavior, and what it's describing is a graph that will eventually rise upward on the right and eventually will fall downward on the left. And that is the graph's end behavior. Go to problem number 4. Find zeros of the polynomial function. Okay, this was the one on the PowerPoint slide. So let's do one that's slightly different here. Let's do a new problem number 4. New problem 4. Let's take f of x to be, let's see, something similar but different. How about x cubed minus 3x squared minus 9x plus 27. Okay, so we want to get the zeros. That means we have to solve the equation when y is equal to 0, find the value of x. Solve this equation for x. It looks impossible. There's an x cubed, an x squared, and an x. You have to factor it. It must be as a product. Okay, so we're going to group these two together, and we're going to group these two together and look for common terms. More obvious here, the common term is x squared. Write down what's left, x minus 3. Now this one, how do you factor it? Well, hint, the entire polynomial down here must still factor. And you already have one factor of x minus 3, so we have to get an x minus 3 out of this. In order to get a minus sign, when here you got a plus sign, means we have to take out a minus sign from both of these terms, and you can easily see that 9 is also a common factor. So 9 times, let's see, x minus 9x, that's a minus 3. Negative 9 times negative 3 is plus 27. See, now we have two terms, common factor again of x minus 3. So we'll factor out the x minus 3 and write what's left. X squared minus 9. Okay, that was the hard part. Now the easy part, set each factor to 0. So x minus 3 is 0, and x squared minus 9 is 0. Solve each resultant equation. X equals 3, so that's the intercept 3, 0. Here, x squared is 9. So x is plus or minus square root 9, which is plus or minus 3. That yields 2 more x-intercepts, 3, 0, and negative 3, 0. Okay, well, we'll only count 3, 0 one time. But note we have multiplicity 2 here, multiplicity 1 here. So the x-intercepts are 3, 0, and negative 3, 0. Okay, let's go on, take a look at problem 5. Find the zeros of this polynomial function. Okay, again, this is the same that we had in the PowerPoint slide. So let's do a slightly different one. Let's do a new problem 5. And let's take f of x to be 2x times x plus 1 quantity cubed times x minus 4 quantity squared. Find the zeros, state whether the graph crosses or touches the x-axis at each x-intercept. Okay, so like we did before. Well, fortunately, we have already factored completely, so we'll take y to be 0. Just copy down the rest of it. Now, we can set each piece equal to 0. So we have 2x equals 0. We have this quantity here, x plus 1 cubed equals 0. And then we have this quantity here, x minus 4 squared is 0. So this gives, dividing both sides by 2, x equals 0. This is multiplicity 1, since it only occurred one time. So the graph is going to cross the x-axis at that spot. Now here you can see 3. Yes, that means we'll have multiplicity 3, because this is x plus 1 times x plus 1 times x plus 1 equals 0. So we get x equals 1 3 times. That's why it's multiplicity 3, and the graph will cross the x-axis. So odd multiplicity 3, odd multiplicity 1, crossing the x-axis at each x-intercept. So this will be at, this is a 1. That intercept is 1, 0. Okay, lastly, we've got this quantity here, x minus 4 squared is 0. That's x minus 4 times x minus 4. So x minus 4 set equal to 0, well, twice will give x equals 4, x equals 4. That means multiplicity 2. That's even, so the graph will touch the x-axis at that x-intercept of 4, 0. So there's a lot of action going on with that polynomial. Fortunately, we don't need to do anything more with it, but that would be a fun one to try and graph. Let's take a look at problem 6. Show that the polynomial function f of x equals 3x cubed minus 10x plus 9. Let's write that one down. 3x cubed minus 10x plus 9 has a real zero, in other words, an x-intercept, between negative 3 and negative 2. Okay, this was not highlighted in the PowerPoint slide. This is, as stated in the objectives, intermediate value theorem. Okay, what does the intermediate value theorem say? Well, it says that if you compute the y-coordinate at one value, and it is, say, positive, and you compute the y-coordinate at another value, and say that's negative, so say this ends up being positive and this ends up being negative, then that means that you are above the x-axis here, below the x-axis here, therefore the graph must have crossed the x-axis between negative 3 and negative 2. Likewise, if you compute the y-coordinate here and it ends up being negative and this one here ends up being positive, then this y-coordinate is below the axis, this one is above the axis, which means the graph must have crossed the x-axis in between. That's why it's called the intermediate value theorem. This theorem is called an existence theorem. It says that the x-intercept exists if you get a sign change in the y-coordinates between two successive x values, but it doesn't say how to find it or where it is, just that it exists. So it's helpful to a point. So let's actually do that. If we compute f of negative 3, we'll have 3 times negative 3 cubed minus 10 times negative 3 plus 9. So let's grind out that y-coordinate. Negative 3 cubed is negative 27. Negative 27 times 3 is negative 81. Negative 10 times negative 3 is plus 30. Let's see, we'll add 9. Let's see, add that together, that's a negative 51 plus 9, so negative 42. Okay, the actual numerical value here is not so important. We have actually plotted a point where x is negative 3 and y is negative 42. But the important thing is that this is a negative value, which means that we are below the x-axis. Okay, so we're looking for a sign change in the computation of these y-coordinates from one value of x to another. So let's come over here and compute f of negative 2. 3 times negative 2 cubed minus 10 times negative 2 plus 9. If we get a negative number, that means this point lies below the axis and there's no sign change, and it shows that there is no x-intercept between negative 3 and negative 2. So we hope for a sign change here. 3 times negative 8 plus 20 plus 9. So that's negative 24 plus 20 plus 9. Negative 24 plus 20. Negative 4 plus 9 is positive 5. Okay, see? So now this is a positive y-coordinate, so we are above the x-axis. So on the number line here, if we are at negative 3 for x and negative 2 for x, at negative 3, we are below the x-axis, turns out negative 42. And if we are at negative 2, we are above the x-axis, turns out at y-coordinate 5. So the only way to smoothly connect this value to this value means that you must have crossed the x-axis somewhere in between the value of x equals negative 3 and x equals negative 2. That's the intermediate value theorem. We don't know where it crosses the x-axis. We simply know it does. That's why it's called an existence theorem. Okay, let's take a look at next problem, number 7. If a polynomial function f is of degree 5, what is the greatest number of turning points on its graph? The greatest number of turning points is n minus 1. So here it says the degree is 5. That means the value of n, the highest exponent, is 5. So it has at most. Doesn't mean it has n minus 1 turns. It has at most n minus 1 turns. So it has at most 5 minus 1, or 4 turns. 4 turns possible, at most 4. It could be 3, could be 2, could be 1, could be none. In fact, if you just want a simple example here, here is a 6th-degree polynomial. Very simple, it's x to the 6th. Its graph looks a lot like a parabola. It's not really a parabola, but it looks like one. And it has how many turns? 1 turn. Yet, it says it has at most 6 minus 1, or 5 possible turns. So see, it is at most. Doesn't mean it has that many. It just depends on what you have. So it's helpful, but not completely definitive. See, problem number 8. All right, use the 5-step strategy to graph the polynomial function f of x equals x cubed minus 3x squared. Okay. First, I take a look at the lead term, so we'll get that, pull that off to the side. The term with the highest exponent, that would be 1x cubed. Okay, so we have odd highest power, positive coefficient in front, odd behavior, odd highest power means that we have opposite end behavior. When x is large and positive, x cubed is large and positive, times 1, still large and positive. And when x is large and negative, a large negative cubed is negative times positive 1 is negative. So it'll be up to the right and down to the left. What goes on in here, we're going to determine over the next few minutes. That requires no math. What does require math is, say, finding f of 0, which is your y-intercept, but this is easy math. So we'll get the y-intercept by letting x be 0. 0 cubed minus 3 times 0 squared is 0. So the y-intercept, that's the origin. Okay. So not only, I'm adding to my picture here, not only does it go up to the right eventually and down to the left eventually, we also have an additional point now right there at the origin. So we're starting to fill in the details. The other thing I like to do right away, because it doesn't involve much math, is maximum possible turns. You see that I vary the order in which I do this because it's a matter of collecting the data, doing what is easy to do first, doing what is more difficult later, amassing all of the data, and drawing your proposed graph, and then finally trying to plot a few points if need be to make it more accurate. So we have the highest degree being 3, x to the third. So the max possible turns is n minus 1. So 3 minus 1 is 2. So it can't turn more than twice. Okay, so it could come from here right up through here and not turn at all. It could go up and turn. Notice if it did that. If it went up like this and turned, it would have to turn again to go back up to the right, and then we get 2 turns. In other words, try drawing a picture here with 1 turn, and you can't do it. So either it has no turns, or it's got 2. No turns or 2. So it could look like the x cubed example that I showed you, or it probably has that shape there, in which case it changes direction here, there's a turn, and it changes direction here, there's a turn, and there's your end behavior upright and down to the left. So one of those two is the case. Let's find some more important information like the x-intercepts. So x-intercepts, so make the y value 0. Okay, so solve the equation x cubed minus 3x squared equals 0. You got to factor it. It's the way it has to be done. Common term is x squared, so factor that. Set each piece equal to 0, so x squared equals 0 and x minus 3 equals 0. Okay, this can further factor as x times x, which means when we set each piece to 0, yes, we get the origin because a y-intercept is also an x-intercept, but key point, multiplicity 2, which means that the graph is going to touch the axis at the origin. Aha. Now, just come up to our picture here for a moment. It has to go and reach this intercept here, which before we thought was a y-intercept. It is, but it's also an x-intercept, and it has to touch it. It means you can't cross it. So it must come up, turn, touch and go down, and then it must turn again to go back up, which will force it right through the x-axis over here at a positive value. So there must be another x-intercept. Let's finish getting our x-intercepts. So we set this piece to 0, we set this piece to 0. Solving this equation gives x equals 3. There it is. There's the other x-intercept. Wonderful. And this is of multiplicity 1. So the graph is going to cross the axis there. No big surprise because, see, the picture as we're generating it forces that to happen. The math reveals it, which is why I said wonderful. The picture and the math have to be in agreement. Okay, let's draw what we have, and then we'll see if we need to improve the details any more. We know that it goes upright. We know it goes down left. We know that it crosses, it touches the x-axis there at the origin, and also at 3 is another x-intercept. And it has at most 2 turning points. Let's see. It must come up, touch, change direction, turn, go through the x-intercept of 3, and back up again. So can we provide any more detail? Here, I can't see my x-intercept. That's 3 right there. Well, yes, this is x equals 3, and x equals 1 and 2 are in there. So I would suggest plotting 2 more points here to figure out 2 more guide points, because this could be far lower. And so let's get that detail. So let's take f of 1 cubed minus 3 times 1 square. So that's 1 minus 3 or negative 2. Okay, so that's 1 common negative 2. That's helpful. That's 1 more point to help make the graph more accurate. Let's find f of 2. 2 cubed minus 3 times 2 square. That's 8 minus, 2 squared is 4. 4 times negative 3 is 12. 8 minus 12 is negative 4. So that's 2, negative 4. Okay, that means we can draw a slightly more accurate graph here. X equals 1, 2, 3. Up to the right, down to the left. X-intercept at 3. X-intercept, which is also the y-intercept, at 0. It has to touch here and it has to cross here. Well, we have two more pieces of information. It has to pass through the point 1, negative 2. And it has to pass through the point 2, negative 4. Okay, so it doesn't go down too far, but see how that helps. Turns there. Turns comes down and picks up these 2 points. Turns goes through your x-intercept and carries on up. So it looks just as it did right up here, except now we have a little more accuracy. And it looks like the low point is at x equals 2, but we don't know that. And if you appeal to the graphing calculator, don't be surprised if that's not the low point. Hand-drawn graph, it's not loaded with accuracy. See if there are any more problems that we need to work on. That was the last one, number 8. So that concludes section 3.2 problems.